so we're sad about this, but let's try to be happy about other things we can do, because actually starting now in some sense, we're going to try to build all the way up to the factoring algorithm. Actually, we're going to take a little bit of a detour later to learn some more stuff about foundations of quantum mechanics, but we're going to get there. And in order to get there, as I said, we kind of want to like build up this subroutine to make it even better. And one thing that we'll particularly try to do, let's ask ourselves another question, is here we were solving this problem called a unique SAT search. And in unique SAT search, that's the version where you're promised that there's exactly one string that satisfies the circuit C. And let's see if we can relax that promise. So can we relax the promise that there's a unique satisfying string? Because honestly, how could you actually know that? I mean, somebody gives you this code C, like how do you know that has exactly one satisfying string? You don't. Now actually, many, many years ago, like 30 or 40 years ago, theoretical computer scientists like figured out like reductions that get around this. So if you just have any old C, they can kind of reduce the SAT problem for C to this special case. But instead of following that, we'll just change the algorithm ourselves to also handle this more general case. Okay, so we're going to actually warm up to answering this question slowly. The answer is going to be yes, but we'll get to it very slowly. So as a warm-up, let's start with a very simple alternative case. Suppose that somehow we knew there were exactly 3 strings that satisfied C. Okay, I picked 3 as like a nice small number. Suppose instead we somehow knew or were promised there were exactly 3. So I'll call them x1 star, x2 star, and x3 star satisfying C. Okay? So this is equally implausible. Like if you just get this black box or this code C, how would you know there's exactly 3? But anyway, let me handle this case, and we'll eventually put everything together. And the goal, by the way, is to find any one of them. So you don't have to find all of them, just find one of them. Now, in fact, what we're going to eventually get to is the following. You should actually think to yourself, this problem should actually be kind of easier than this problem because there's more things to find. Here, there's only 1 out of the 2 to the n things to find. Now there's 3 out of the 2 to the n things to find. So actually, not only should we be able to solve this, we should be able to solve it like a little bit faster, ideally. And that's what we'll find. But for now, let's just think about solving it. And then once we solve it, we'll be like, C was a little bit faster even than this case. And we're going to become interested in like how much faster can you do it. Because with the classical algorithm of just like, I don't know, just start guessing strings, plugging them into C, see if they satisfy them, you should be able to do this one maybe like 3 times faster. Okay, so to tackle this, we're going to just basically start repeating the analysis of Grover's algorithm from last time. Since we did it, we're going to be a little briefer, and then we'll just see sort of what happens. Okay. So once again, let's see. We're going to start by making this uniform superposition vector, which again is 1 over square root d times all 1s. Okay, whereas always d stands for 2 to the n. And then we're also going to imagine, this first step is to apply if f then minus. So that takes us down here. So let's work that out. We do if f then minus. And what do we get to? Well, it's a similar thing, except now there's 3, special unknown coordinates that get flipped to negative. So we're going to still call the resulting vector of using notation cat f. And it's going to look like square root 1 over d times Well, it's going to be mostly 1s, but then there's going to be some -1, and some other -1, maybe some other -1, but the rest 1s. Okay, and this is going to be in like the x1 star slot, and this is going to be in the x2 star slot, and it's going to be in the x3 star slot. Okay, so it's mostly 1s, but there's 3 -1s. Okay. Now again, we're going to kind of make the same observation that 3 is still a small number. So this vector of all 1s and this vector, which is pretty much all 1s, are practically the same vector. They're extremely microscopically close. So let's look at that again. So we're going to subtract them. And this one is not a unit vector. It's not a state vector, but it's still a vector. Okay, so we're going to get like 3 2s in our vector. So let me factor out the 2. We'll get 2 over square root d times vector. That's almost all 0s, but it has like 3 1s in it. And again, they're in the same slots, x1 star, x2 star, x3 star. And so we can write this as 2 over root d times, well, let's write it as 2 over root d ket x1 star, oops, plus 2 over root d ket x2 star, I'm running out of room here, plus 2 over root d x3 star. Right, because x2 star, that stands for the vector that's all 0s except it has a 1 in the x star position. Okay, so this is what we can think of. So this is kind of a cool vector. It's the vector that has equal, well, this vector has equal amplitude on the 3 satisfying strings. So let's actually define the natural, and that's this blue vector here. Let's define the natural unit length vector, the state vector, that has the same property. It has equal amplitude on all 3 satisfying strings. So it's going to be just like a scaled up version of this vector. I'm going to erase this because it kind of looks confusing. And I'm going to give it the name, the suggestive name of ket goal, for reasons we'll see in a moment. And that's just going to be square root a third x1 star plus square root a third x2 star plus square root a third x3 star. Okay. So this is just like a length 1 version of this vector. And so it's what you get if you just like scale this up into this length 1. So in fact, let me just adjust this diagram. This is going to depict goal. So let's make write down some facts about this vector. Okay, so first of all, it is a unit vector. So the sum of the squares of the amplitudes is 1, like it should be. So it's a proper state. And it's also like a good goal, because suppose we manage to get our, quantum state to be exactly ket goal. Then what happens if we, extract all or do a measurement? Well, then with 1/3 probability it prints out x1 star, with 1/3 probability it prints out x2 star, 1/3 probability it prints out x3 star. And that's great. These are the 3 satisfying strings. We're only trying to find one of them, so whichever one it prints out is fine to us. Okay? So if we get the state here, then we measure or extract all. We get a uniformly random satisfying string. Okay. And the last thing I just want to calculate is how do we write this vector, unif minus f, in terms of goal? As I said, goal is just a scalar multiple of this unif minus f. And what is the scalar multiple? Well, you can compute it. I'll just tell you or we'll check. It's 2 times square root 3 over d times goal. Okay, you can just check that. If you take this goal and multiply all the coefficients, or the amplitudes by this, 2 times square root 3 over d, you get back to this. So, yeah, sorry. So what does this tell us? Well, one thing is that this difference vector, we know its exact length. Because goal is a unit vector, so this is its length. 2 times square root 3 over d. And same as before, this is saying that goal is a linear combination of unif and f, which means it's in the subspace of unif and f. So just as before, this picture is legit in the sense that this vector is indeed in the two-dimensional plane spanned by those two vectors. Write that. Goal is in the 2D plane of unif and f. Okay. So this is super great because it's pretty much exactly the same picture. It's pretty much the same picture. There's almost no difference. The only differences are that, well, we used to have x star up here, and now we have goal, which is kind of like the uniform combination of the three strings we're searching for. And the angle is a bit different. The angle is actually a bit larger. So this is basically the same as Grover. So I'll just summarize the two differences. X star is now goal. But still, I mean, our goal is to get to that state vector, because then when we measure, we get what we want. And the angle between unif and f, well, the angle theta is the length of this arc in radians, which is, these are still extremely small numbers. So it's basically the length of this difference vector, which we saw as 2 times square root 3 over d. So is now theta, which is extremely close to 2 times square root 3 over d. And we'll put this in a little box because this is the difference. This used to be 1 when there was one satisfying string. And I think you can probably check that if there's like 7 satisfying strings and we repeated this, this would be a 7 here. Okay, so now we can basically just do the algorithm as we did before. So if we make R as before, which is the combination of these two reflections, the one if f then minus and the reflection through uniform, then we just need to, if we start at uniform as before, how many times should we repeat R? Well, it's the same as before. Sorry, uniform, and we repeat R for basically 90 degrees over theta times. And this is like extremely tiny, like fudging. Like this pi over 2 should really be like 90 degrees minus half of theta. But theta is exponentially tiny, so it's not a big deal. And theta is not literally this, but it's exponentially close to this. So it's pretty much this. You have to round this off to an integer. But all these differences are super minor. Then we'll get extremely close to goal. Okay, and how many times is this? Well, it's the same. We have pi over 2 divided by theta. So you still have like pi over 4 like before. But now, instead of square root d, we have square root d over 3. Or, you can call this, okay, the pi over 4 is not a big deal. It's a little bit less than 1, but it's, well, let me write it. Pi over 4, square root 2 to the n divided by 3. And as I said, actually, this is kind of nice. It's a little bit faster than Grover, right? Grover, you repeated it like pi over 4 times square root 2 over n. And now you only need to repeat r, pi over 4 times square root 2 to the n over 3. So this is somewhat faster. It's faster by a factor of square root 3. Okay, and why is it 3? It's because we started by assuming there's 3 satisfying strings. And what I'll show somewhat later is this is, generally true. If there are s satisfying strings, then you actually can do Grover's algorithm square root of s times faster. And we're going to get into that. Any questions? Exactly. We're going to get exactly into that question. It makes sense because, initially we assumed that there's exactly 1, and now we're assuming there's exactly 3. But like for both, how would you know either of these are the case? So eventually we're going to build up to this situation where even if you don't know how many satisfying strings there are, we're still going to get like a fast version of Grover. Like it'll kind of figure out how many there are, roughly. And then we'll eventually see that like if there are s satisfying strings, even if you don't know what s is in advance, you can still get an algorithm that takes like square root 2 to the n over s. So here we just thought that if you do know that s is exactly 3, you can get square root 2 to the n over s. Mm-hmm. Oh, great question. Yeah, let me address that question. So the question was like, the 3 is a bit funny. Let's go back to the case where like you believed or you were promised that there was exactly 1 satisfying string. And if that's true, you run Grover's algorithm and you find it and everything is cool. Now the question is like, what if like that was a lie and it turns out that, for example, there were 0 satisfying strings? So I'm going to give 2 answers to this question. One, we'll see what actually happens if there's 0 satisfying strings. And 2, well, I'll say a second answer now, which is one thing that you can always do when in the context of SAT is you can run an algorithm that tries to find a satisfying string, or that's supposed to find a satisfying string. But at the very end, like when the algorithm's like, okay, here's what I believe is the satisfying string, before you just like blurt it out as your final output, you yourself can check easily if it's a satisfying string. Because now you have the string, you're like, I also have the code C, I will just plug the string into C and see if indeed it outputs 1. And if it does output 1, then you're like, oh great, everything is cool. This is indeed a satisfying string, I found it. And if it doesn't output 1, well, one of 2 things can happen. One, even in Grover, like you never, because you have to round this off to an integer, like you never literally get exactly to ket x star, but you might get like far away from it, but like an exponentially small amount. So there is like some, exponentially small chance that everything was cool, but just the measurement, failed with exponentially small probability. So since you always have that in the back of your mind, it's never going to happen because 2 to the n is super tiny. But okay, if you always have that in the back of your mind, then when Grover spits out a string, you test it in C to see if it's satisfying. If it is, great. If not, just run it again. I mean, you can run it like 10 times. And this exponentially small chance is definitely not going to hit 10 times in a row. But if it does hit, like if you run it 10 times in a row and like every single time it's not a satisfying string, you could say like, hold up, I think I've been lied to. Like, it was written on the board, like I promise you there's 1 satisfying string, but like I'm pretty sure there isn't. And that's cool because what you can infer from that is that with Grover's algorithm that we've seen so far, you can actually do a little bit better than solving the unique search problem. You can solve a problem where like the promise is either there's exactly 1 or there's exactly 0. And the task is, first off, tell if there's exactly 1 or exactly 0. And if there's exactly 1, please find it. You can actually solve that better problem. Why? You just say to yourself, I'm going to pretend as though there were exactly 1. And I'll run Grover's algorithm. And if it finds it, then great, I'm done. And if it doesn't find a satisfying string, it must be that there's exactly 0. Because if there were exactly 1, I would have found it. or would have found it with, except with exponentially small probability. So what this kind of means is, like, whenever I'm always saying like things like, oh, if you somehow knew there was exactly 3, then you could find one in this amount of time. You can always do a little bit more. You can either find one in this time, or kind of confirm to yourself that there weren't exactly 3. Yeah. That's a good question. If you're told, what if you're told there's exactly 1, but there's actually 3? That's exactly what we want to get into in this lecture plus the next lecture. So indeed, we're eventually going to get to a state where the final version will be like, you give me a code C. I don't know anything about how many satisfying strings it has. I will, first of all, find out roughly how many satisfying strings there are, and also find one satisfying string in about like this time. Or if there are 0 in about square root 2 to the n time, I will be like, there's 0. Yeah. It is done by some kind of binary search, as we'll see. We'll get to the binary search next time. That's a great observation. And you can even think about it a little bit. Like, it's like you have this picture. You can set up this picture, but you don't know what theta is. So like, you can always set up this picture, as we've done before. And like, in the first case, we were like, and by some magic promise, you know theta is like basically 1 over square root d. And now we're like, oh, by some magic promise, you know theta is like square root 3 over d. So eventually we want to tackle, what if you don't know what theta is? It could be anything, like a mystery rotation amount. Can you sort of learn what it is? Indeed, we're going to get to exactly that. Finally, it's also interesting to just ask, like, what does happen if you set this up when there are no satisfying strings? So you tell me, what happens if you do set this up and there are no satisfying strings? Like, you think there are 3, and so you run this algorithm. What happens? That's right. Uniform minus ket f is all zeros, which means it doesn't rotate at all. That's right. So you prepare a uniform, and then you do if f then minus. But f, now we're imagining there are no satisfying strings. F is always 0. So that's like, you don't do anything minus. So in this case, like if f then minus is like a no-op. It literally does nothing. So then you do uniform. You do if f then minus. Nothing happens. Then you do this like reflection through uniform. Still nothing happens. So R is like rotating by 0. So you just like stay at uniform the entire time. And then finally, I suppose you do extract all at the very end. And what happens when you do extract all on the uniform, ket uniform? You just get a uniformly random string. So that's what happens if there happen to be no satisfying strings. And then, like, probably you will, in the context of SAT, you'll take this output and you'll be like, hey, maybe I was in the good case. Like, maybe there really were 3. So, like, as a final check, I'll plug it into C, what the extraction output was. I'll plug it into C and see if it's satisfied. And, except with a teeny tiny probability, or in fact, it'll never satisfy. You'll be like, oh, wait, it didn't satisfy. Yeah. All these are exactly the kinds of things we're going to do. So like another feature is that, well, you can think about what to do, but like maybe you'll first like try to imagine maybe theta is big, and you'll do a few rotations and see if that works, and then you'll do a few more and see if that works, and do a few more if that works. There's one extra feature of this problem, which is that like the number of satisfying strings is either at least 1 or it's 0. So that means like theta is either 2 times 1 over square root d, or it's 0. So somehow there's like a smallest non-zero value of theta possible. So if you kind of mess around and kind of think to yourself, man, theta is like smaller and smaller. Theta is pretty small. If you eventually kind of convince yourself that theta is smaller than 2 times 1 over square root d, then you're like, well, the only other possibility is that it's 0. But indeed, we're going to get into all this. So this is great that it came up. And so in fact, think about it. Like you can now think about like how would I solve this SAT problem if I didn't have any information about what theta is. That's exactly what we're going to do.